Hello, this is Philip Seagraves with Georgia State University. Going to do some Excel statistical functions. We're moving beyond the basics of standard deviation and variance and covariance, and now we're going to take a look at a couple of the curve-related functions and help demystify how these things work in Excel. First, let's take a look at our classic normal distribution. By the way, this drawing is not of my original creation. It comes from the Hawaii.edu website in the math department. It looks like it comes from Math 100 class, kind of your basic statistics class. And we have a normal distribution here where we have from -1 standard deviation to +1 standard deviation, approximately 68% of the area under the curve, and about 95% from +2 to -2 standard deviations, and about 99.7% from 3 standard deviations up to +3, from -3 to +3 standard deviations. So let's see if we can make Excel spit out some of these same figures, and let's learn how it works maybe a little bit differently from the way you might expect it. But you'll figure it out and pick it up pretty quick. The first function is the NORMDIST function, normal distribution function, or a Z distribution. And when we take a look at how this function works, it's the typical equals to begin a function, the function itself, open parentheses, and close with some parameters in the middle. Let's click on it and see what we're talking about here. First is the function, then we have x, which is the value of interest that we want to get a probability for. We have the mean, the standard deviation, and a yes/no on whether we want to deal with a cumulative. And we're going to leave this set on cumulative so you'll see how this function works. The x is the value of interest. In this example, we'll use 10 as our mean, a standard deviation of 2, and a value of interest of 12, which will be exactly 1 standard deviation on the plus side of our mean. And we would expect that +1 to -1 gives us 68% of the area. So what does Excel provide us? It gives us 84%. And 84% is what is called a cumulative probability, which is everything from -infinity in our distribution up to the mean, and then up 1 standard deviation. So everything to the left of the mean is always going to be 50%, plus the rest, which is going to be half of our 68%, or about 34%. So if we add 34 plus 50%, we get 84%. So everything to the left of this point is 84%. Well, how would we get it to tell us the area under the curve at this point? Well, just for this example, if we leave our same figures of 12, which is here, 10, which is our mean, 2 standard deviations, and we subtract the 50%, that's only going to leave us this piece of the distribution here, and we double that, which would get us the 68.26%. So you can see how you can back into some of those functions in Excel. Well, what about a standard distribution? This one's nice because all we have to do is provide it our Z value, and it'll give us our probability. Again though, and you don't have the choice this time, it's always going to give you the cumulative. So if I put 1 standard deviation, it's going to take me from -infinity on the minus side up to the mean and up to that point, which is going to give me 84%. Well, what do you think is going to happen if we put a -1 right there? Aha! It's going to give us a 16%, which is everything just to the left of this range. So it's cumulative up to the -1. If we make this 0, it's going to be 50%, because that's our mean. So it's cumulative up to the mean. Let's take that back to 1. And just like we did before, if we subtract 50% from that value, we're going to get just this part here. We double that and we'll get our 68.26. I'm just trying to show how you would get it back in this notation that we're used to seeing, this 68% under the area under the curve for -1 to +1. And then how about our t-distribution? Well, we know our t-distribution is going to be a little bit flatter and a little bit more spread out, so the tails will be a little higher and the peak right here in the middle would be a little bit lower, at least for small sample sizes. So how does a t-distribution work in Excel? The t-distribution asks us for the x, which is going to be our number of standard deviations, and our degrees of freedom, which in a univariate case is going to be our sample size minus 1. So how big would our sample size be here? 31. That's why we have a degrees of freedom here of 30. And the number of tails. In this case, we're going to have our tails are going to be out here and out here. So what is it giving us? 33%. Well, 33% in the t-distribution function of Excel is only what is outside of those standard deviations on both sides, because we chose a two-tailed. Now, to get that in the normal, in the notation or the types of figures we're used to dealing with, we would simply take the inverse of it. So 1 minus this t-distribution as we had done it before, with an x of 1, which is 1 standard deviation, 30 degrees of freedom, and 2 tails. So as you can see, the area under the curve with a t-distribution is a little bit smaller, as we would expect. Well, what about these norm inverse functions? Well, they just kind of give us the opposite. Instead of providing a value of x, as we do up here, which was that number 12, which we used several times up here, or down here we gave it the t value, it's going to give us the opposite. It's going to give us the value up here of this point. This one's going to give us the z-score when we go down here, and the other function, the t inverse, will give us the t. So we get a z value here instead of providing it. We'll get a t value down here instead of providing it, and we'll get our value of x down here instead of providing it, as we did up here. So how does that work? So we have our norm inverse function. We're going to provide it the cumulative distribution, which is everything on the left-hand side of the mean, this entire tail, so 50%, plus that additional value that we had here, that 34.13%, or half of the 68.26, which would be 34.13. So when we add that and we use our mean and our standard deviation, voila, it gives us back this point right here of 12. And to get to that 0.8413, as we've done up here, it'd just be a real easy 0.6826 divided by 2, which gives us half this range. Then, of course, we would just add 50%, and that would get us the 50% plus the 34.13 to get us up to that point. And very similarly, to do the norms inverse, just as it was easier up here, all we provided was the z. Up here, all we provided is that cumulative probability. This entire area under the curve plus what we have up to this point. So the half below the mean, 50%, plus the amount that we have up here, totaling 84.13. Gives us our z of 1 standard deviation. As we did above, we simply take the 0.6826, divide that by 2 to give us half of this range, and then we're going to add 50% to that, or 0.5. What about t? Just as up here, it works a little bit differently. In this case, we're going to provide the t inverse function the amount of the area under the curve both out here and out here. So the sum of the area outside of the curve, because the t inverse function always assumes two-tailed distribution. So it's going to need what's both down here plus what's up here, which in the case of a t is about 32.5%. We have about 67.5%, which is under the curve when you have +1 and -1 standard deviations with a t distribution. And of course it spits back the t, which is 1 this way and 1 that way. Well, how would we maybe use some of these functions in a real world, maybe not such a real world scenario, but one that might be just a little bit interesting to play with? Let's say I've got a 5-hour drive. I've gone thousands of times from Atlanta, Georgia down to Savannah, Georgia. A great place along the coast, beautiful place to visit. And of all these times, I'm a stats guy. I've been tracking, I've been keeping a great log of exactly how long it takes me. And I've calculated, I pulled out 30 of those. Let's say I pulled out 32 of those. And I came up with a mean hours, or an average hours, to drive to Savannah of 5 hours. And my standard deviation is 30 minutes, or 0.5. So now I'm in Savannah, and it's early Monday morning, and I've got to get back and teach a class at Georgia State on Monday afternoon after this nice vacation weekend. So how much time do I need to leave to make sure I'm there on time to teach my class? So let's set this up. We have 5 hours as our average, 30 minutes or 0.5 hours is our standard deviation, and this is where we're going to plug in and try different amounts of time allowed for the trip. I've actually used a spinner function over here to make that easy. I'll show you how to do that. Let's view our toolbars and let's turn on our control toolbox. And right here is a function called a spin button. When I pull up the spin button function, I can draw a spinner anywhere I want. It put a nice big one right there. I'm not going to use that one, so I'll delete it. But I'll take you into this other one that I already did. Now if I right click on that, I have format control. Now when I format control, I can tell this button to change a number anywhere on my spreadsheet when I click up or down. It's going to set a minimum value of 0, maximum value of 1,000, and incremental changes of 15. These can only be whole numbers. So that's why I couldn't put hours in here and have it go up by 0.5 hours or 0.25 hours, something like that. So I just put minutes here so I can change the minutes up and down in increments of 15 minutes. So each time I click this up or down, it's going to add 15 minutes, and over here, since I divided this number by 60, it's going to go from 6.5 to 6.25 and so forth. So we'll cancel that out. I'll show you how it works. We just kick this button up and down, and let's take a look at our functions. We have the norm distribution function. We have our x, which is the hours that we're going to allow. We have our mean, which is the mean hours from our sample. We have standard deviation, which we have right here. And we have true, because I want that to be a cumulative distribution. Because if you remember, we're not concerned about being too early. We just don't want to be late. So we want to know what's the area under one side of the curve. And actually what we're really looking at is we want to know what's out here. Not the area under the curve, but maybe 1 minus the area under the curve. So the chances of being on time are 99% if I leave 6.5 hours. The chances of being late are going to be 1 minus that, as I was just saying. So 1 minus the chance of being on time is 0.1 in this case. So we can change the hours up and down. Let's see, if I leave 5.5 hours, there's about a 16% chance of being late. And very similar, we have the t distribution down here, and all we've done with the t is it will give you an error if you allow a negative value in here for your number of standard deviations. I've used the absolute value, and I've had to calculate how many t's or standard deviations we are away. So I've taken, in this case, I have taken the time allowed for the trip, subtracted the mean from that, and I have divided it by the standard deviation of our sample. And since I said earlier we had a sample of 32, we have a degrees of freedom of 31, and we have a one-tailed distribution, just like I was talking about before. It's cumulative in the case of a normal, but we need to tell it a one-tail in the case of a t. And we'll see the t calculates. In this case, it does calculate the percent chance of being late, because remember, it's calculating what's outside the distribution, the tails, which is different from the way it works with that z distribution. And so then we get the chance of being late as our function, and we just do the 1 minus that to give us the chance of being on time. So that's the way these functions work in Excel, and we can just kind of crank these, and we see that if I leave exactly, I'm going to be late half the time. Alright, well hopefully this helps you understand those functions. Excel is fun, it's powerful, it can do a lot of great statistical things, and hopefully this has helped you to become more a master of stats in Excel. Have a wonderful day. Thanks. Bye.